that are about galactic winds in a different context. And there are galactic winds that are driven by supernovae. So as we know, supernovae are responsible for a lot of effects and characterize a lot of properties of galaxies. And they are responsible for shock heating, acceleration in the ISM. They drive turbulence, they drive wind, and they can also create super bubbles in low density regions of galactic disks. And just to give you a number, but you know probably, is that every supernova remnant injects something like 10 to the 51 ergs of energy in form of ejecta that move at high speed initially, and that coupled to the ISM. So in our work, we try to build a bottom-up approach to studying the effect of supernova feedback in galactic disks. And so this is our story so far. And it sort of started a few years ago when we decided to review the momentum and thermal energy injection from individual supernova remnants, which also several groups tried to do. Basically, the results from several groups were all in agreement, which was pretty good, actually. But so in our group, we basically build a subgrid model that describes, given a set of properties of the ISM, what is the momentum and thermal energy injected by a supernova remnant. And from that, we sort of moved up to scenarios of growing complexity, because we really wanted to study what effect do supernova have on the properties of galactic disks. And so we went to the next step, that is basically like turbulent boxes with multiple supernovae, and in particular stratified boxes that mimic really tiny portions of a galactic disk, with the goal of studying turbulence and studying the driving of winds. Basically, during that study, we figured out that those simulations actually have a lot of limitations. They are quite important, and they were not appreciated too much in the literature. And so in the last few years, and this is a paper led by Drummond, we developed a set of simulations that overcomes the problems of the previous ones. So I will start by talking about a little bit how we inject supernovae in the simulations I'm doing. So I have a grid code. It can be whatever grid code you want. And basically, I consider a patch of the ISM. I measure densities, metallicities within a sphere of radius r. And given the analytical model that we developed, we can predict, given these properties, what's the radial momentum and the thermal energy injected by a supernova remnant in isolation in this medium. And this is very similar to what fire does. The difference is the implementation in a Eulerian code, basically. So we had to take into account that we are actually working on a grid, and we had to figure out the proper weighting for this. Anyway, so the interesting part is when we actually talk about the physics of galaxies here. So this is the local simulation we ran a few years ago. The idea is to consider a 1 kpc patch of a galactic disk and set up a local approximation, in which we assume that the potential only varies along the z-axis, and it's imposed externally. So it's a fixed and static potential in time. And so essentially, we prescribe a certain recipe for the driving of supernovae in the disk. And what happens is that maybe this should play. Okay. So we drive every single supernova that should explode in the disk according to this model. And you can see this tiny explosion in the disk, which have basically high density, so that the effect of the single supernova remnant that explode there has limited effect, but you also see that some of the supernovae explode close to low density regions which drive winds. And so this brings me to some of the successes of these simulations. The first success is that you can actually drive a galactic wind successfully here. And in particular here, I'm showing the mass loading of this galactic wind for one case that we analyzed. And as you can see, it's a sort of quasi-steady state in which there's always gas moving, flowing out from the disk. And the other result that was kind of interesting is that, again, we self-consistently develop a turbulent disk with a velocity dispersion of 30 kilometers a second. And so in this 2016 paper, we analyzed the properties of turbulence and the properties of the winds. The problem is that the winds in these simulations have some limitations, and this is what basically pushed us to improve our setup. So this is the first limitation, and this is actually intrinsic. It's not numerical in its nature. It's actually a property of when you set up a problem like this in plane parallel geometry. So basically you have a potential in a system that only has 1 degree of freedom, so it varies along the z-axis, perpendicular to the disk. And you can also demonstrate it analytically, but essentially when you drive a wind like this, you end up with a constant sound speed in the wind, and the wind cannot become supersonic, so it never accelerates to the speeds that should be observed in real galaxies. And again, analytically, you can figure out that if you actually work in spherical geometry, you can end up with a wind that instead has the property of expanding adiabatically, which also drives the sound speed in the wind down and allows the development of a sonic point beyond which the velocity of the wind is supersonic. And so this actually might reconcile these kind of simulations with observations. So the next thing we did was to develop a setup for this problem, basically, a problem in which we have a better geometry for the system. The second issue that those simulations have, the local ones, is that if you consider boxes of different heights and you look at what's the mass loading at different heights, it actually has some limitations. It depends on the height. And that's actually a series of problems related to lack of sonic point, the idealized potential that doesn't have a well-defined escape velocity, and idealized supernova seeding that basically doesn't consider clustering. So we improved all of these, and we basically kept the same resolution of a few parsec, and we went to basically global disks. So that developed a galactic wind. Basically, the driving wind model is the same. Supernovae explode in the disk. They drive this galactic wind that now can expand. It can flow supersonically. And this is the demonstration that this happens. As you can see in the dashed line, you see the sound speed decreasing as the wind expands. And you can see that the velocity of the wind saturates. And the other great thing is that in this case, as a function of radius, distance from the disk, the mass loading also converges because we have a well-defined escape velocity, so we can actually allow the gas to escape the galaxy. And one interesting thing that you can do with this kind of simulations, which are very simple in principle, is that they're not very expensive, and you can vary some of the parameters of the simulations, like the surface density of the disk or the way you drive supernovae, and you can sort of figure out what's the physical picture in terms of some parameters. So the physical picture is the following, apparently. So if we are in a disk and a supernova explodes on a scale that is too small compared to the scale after the disk, if the cooling time is too small, it will just cool down. But if the supernova explodes in a region of the disk where the density is low enough, the cooling radius is large, Okay. We're back. All right. Thanks. Okay, so the argument here, again, was that basically supernova remnants with a cooling rate that is comparable to the scale height of the disk will contribute to the wind. If you put that in, you get a scaling for the energy loading of the wind, and that depends on the clustering of supernovae. So the more this FCL parameter increases, the more supernovae are clustered, and the higher the energy loading and the mass loading is. And this is actually something that we can do with the simulations, and we can predict from this simple analytical model, and the results match quite well. So essentially, if we want to really achieve realistic galactic winds, the next step to do is to go to a very realistic model for the clustering of supernovae, which will drive up the mass loadings to even higher values, which are more consistent with observations. And ideally, this will also allow us to study the phase structure in these galactic disks in more detail. And now this froze, so I cannot skip to that. Okay. So these are my conclusions. Essentially, we sort of built a series of simulations that successfully develop galactic winds. They have the right properties for the galactic winds. And the next step we are trying to do is to go to more realistic models, which supernovae are driven more realistically. Okay.
Time for a couple questions.
Yes.
So, if I understand right, the new geometry doesn't affect the turbulence injected into the disk, or is there a funny effect because the wind?
It's the same amount of turbulence, actually. Like it's very similar. So these simulations actually don't have self-gravity, so you cannot drive really high turbulent motions with gravitational instability, for example. And so the velocity dispersion always stays like at something like 10 kilometers a second, but it's more or less the same.
But the energy efficiency over a mass loading to a plant, then if I was right, the energy efficiency is 1%.
Yeah.
Which is used for our simulations.
Yeah, but again, you can actually boost it by invoking better clustering, and so like that's why, yeah, and I think that's included in cosmological runs. You know, so yeah.
And it's only.
I'm just curious, how do you think about vehicles in some relation patterns in big clusters, and they were the short, not one, million. When you win. It's not clustering, it's a model of clustering.
Yes. The way we set up that, our problem initially was to look actually at the explosion of a remnant in an inhomogeneous medium. So we took into account that there are inhomogeneities driven by, for example, turbulence driven by other supernovae. So that's sort of take into account what already happened in the medium. I agree that it should be, well, we should probably also do cluster simulations in which we explode multiple remnants locally and figure out if the momentum and thermal energy budget is what we predict here, but yeah.
All right, thanks very much.
Okay.
Now we'll move on and hear about some observations.